So let's start. Let's start with functions. So, what is a function? Before we wanted to talk about that, I think we had a little bit of an intro, a little backstory.
Hmm.
Maybe you want to start with that, Parker.
Yeah, I think we talked about this a little bit when we were doing, uh, when we were talking about proofs and things like that, or types of numbers. I don't remember. But so it's important to know. This is very basic. What an ordered pair is, and so essentially, an ordered pair is just, well, it's in the name. It's ordered, meaning the order matters. And then there's two elements in that pair. And the two elements don't have to come from the same set. For example, you could have the first element in the pair is a real number and the second one is an integer. It doesn't matter. But as long as the order is preserved and they come in a group. For example, everybody knows what a graph is. If I tell you the point 1 comma 2, you can kind of imagine where that is on the graph. It's not the same as the point 2 comma 1. That's kind of in the sense that it illustrates how the order matters of the pair, right? So that's pretty much what it is. But you can put anything, right? You could put a duck and a bear, right? It doesn't matter what the elements are or what sets they come from, but yeah, you just put them, boom, in a group together, and there you go. That's what an ordered pair is.
And the main reason this even becomes important is because here we start to understand the relationship between these two sets, right? That's I guess I don't know really where the bear and the duck would come from. Like I don't really know if that's the best example.
Maybe
of
like
an ordered
predator
pair.
and prey or something like that.
No, I mean okay. I guess no, that is valid. I guess it could describe a certain set, but again, the main idea is just to see what is the relationship between the first and the second variable in this situation. So in the situation where we have pairs, well, there are only two variables to consider, and that's usually when we picture in our head, we're thinking of that 2D graph, right? Because we're usually thinking of ordered pairs. We're thinking of only two numbers. So we start with that and we're like, okay, well, this is one ordered pair. Let me list every single ordered pair from this set, right? Now, the set might have many, many variables, many numbers, as you said. One can be real numbers, one can be integers, right? So every single pair that go together and you graph them out, and then that gives you some type of relationship, right, between both of those variables or both of those sets. And that is
Yeah.
what we call a relation.
So relations can be pretty chaotic because there's not really a rule. Well, there is a rule, but there's no like restrictions, you know what I mean? So for example, if you have a relation, and by the way, a relation is a set of ordered pairs. And what makes it a relation is that the first variable has some connection to the second variable. So for example, we have our set of ordered pairs where the first element is like a person. So it's from the set. The element comes from the set of like people, and the second variable is a city. And the relation between the first and the second is that the person has once in their life lived in that city. So clearly, this is not a function because one person can live or can have lived in multiple cities, right? So every input does not have a unique output, but you can still call it a relation because you can put all of these pairs of people to cities in a bag, in a set, and that entire set is a relation.
And well, why is it not a function? Again, that function is very specifically defined, right? Because I think we kind of gave a little thing there, Parker. You mentioned that it's because one person could have lived in many cities. So, well, how is a function defined? That's inherently defined, and I think we're going to get into this definition soon, of injectivity, right? If we have these two sets, one point from set A, let's say we have set A and set B. So one object from set A cannot point to more than one object in set B. And that is simply a characteristic of what we call a function, right? So every output has a unique input. Yes. Because, and that's the whole idea of injectivity, right? Parker, you have a questionable face on it.
I don't, wait, I don't.
Is that not it?
I don't think injectivity is like necessary for being a function.
Yeah, but
I think it's
but
a property
if
that
it's
a
not
function
injective,
can have.
if it's not it's a property of a function, yes, but if it's not injective, that means one point again can point to two different points, which just inherently does not make it a function.
Right. So I'm just going to clear something up here.
Yeah.
So Ray, it's the reverse of that, right? So you can have two inputs. Pardon me. Two inputs going to the same output.
That's
right?
fine. No, that's fine. That's fine.
Yeah,
I'm saying one input goes into two outputs. That's not a function anymore.
Yeah, so that's not injectivity. The first thing I say would be injectivity.
Mm-hmm.
Oh, is that the other? Okay, I think we're confusing.
Yeah, don't worry. Just So there's a unique output for every input, but there's not a unique input for every output.
Yeah. But isn't that injectivity? Because injective.
So don't worry. This is the first. The first thing you stated is an ejective function, right?
Yes.
But the other way around is not necessarily true. You don't need that. You just need one output for every input. You don't need one input for every output.
Okay, that makes sense. Okay, that makes sense. A little clarification there on those functions for those.
Yeah,
for
like
those people.
The condition that you stated is necessary for being a function, but it is not called injectivity, right? So if it's a function, then every input doesn't necessarily need an output, but if it does, then it's unique. Or not unique, there's only one of them. There's not two outputs for one input. And okay, just to clear this up, it's pretty much called the vertical line test.
Yes.
If we're talking about like one.
But this also only works in I guess it works in higher dimensions too, but it's a lot more visible in your 2D. Like your vertical line test, right? Exactly. Mm-hmm. So what is a vertical line test? Maybe just explain it a little bit.
Well, if you put a vertical line along your graph and you sweep it, if at any point the line intersects the graph twice, then it's not a function. It has to just intersect the graph of the function one time for every single point.